Stellar mass is a fundamental property of stars, representing the total amount of matter contained within a star. It is one of the most critical parameters in astrophysics, governing nearly every aspect of a star's behavior, life cycle, and interactions with its surrounding environment. Measured in units of solar masses, where one solar mass equals the mass of our Sun, stellar mass is a central concept for understanding the physical characteristics and evolutionary pathways of stars across the universe. The mass of a star is the primary determinant of its physical structure, energy generation processes, and evolutionary fate. It dictates temperature and luminosity. Stellar mass governs the temperature and pressure at the star's core, which in turn influence nuclear fusion rates. More massive stars have hotter cores and produce energy at much higher rates, resulting in greater luminosities. Massive stars consume their nuclear fuel rapidly due to their high energy output, leading to shorter lifespans. In contrast, lower mass stars burn their fuel more efficiently and can exist for billions to even trillions of years. The ultimate fate of a star, whether it becomes a white dwarf, neutron star, or black hole, is determined by its initial mass. A star's mass influences its transition through different stages of stellar evolution, such as the main sequence, giant phase, and supernova. A star's mass affects its gravitational pull, which impacts the dynamics of binary systems, planetary orbits, and the formation of surrounding structures like star clusters and galaxies. Determining stellar mass is not straightforward, as direct measurement is often impossible due to the vast distances involved. Astronomers rely on indirect methods, primarily binary star systems. In binary systems where two stars orbit a common center of mass, astronomers can use Kepler's laws and Newtonian mechanics to calculate individual masses. Observing the orbital periods, velocities, and separations of the stars provides critical data for mass determination. Theoretical models of stellar structure and evolution are used to estimate mass based on observable properties like luminosity, temperature, and spectral type. In rare cases, the mass of a star can be inferred from its gravitational effect on the light of a background object, as predicted by Einstein's general theory of relativity. When a star's planets transit across its surface, subtle gravitational interactions can provide estimates of the star's mass. For stars on the main sequence, there is a well-defined correlation between mass and luminosity. This relationship allows astronomers to estimate mass indirectly from observed brightness. Stars span an enormous range of masses, from tiny brown dwarfs to gargantuan supergiants. Objects with masses below about 0.08 solar masses are considered brown dwarfs. They are not massive enough to sustain hydrogen fusion in their cores and are often referred to as failed stars. Stars with masses between 0.08 solar masses and 0.5 solar masses, such as red dwarfs, are the most common type of stars in the universe. They are long-lived and burn fuel efficiently. Stars like our Sun, with masses between 0.5 solar masses and 8 solar masses, have lifetimes of billions of years and end their lives as white dwarfs. Stars with masses above 8 solar masses are rare, but dominate in luminosity and impact. They have short lifespans and end their lives as supernovae, often leaving behind neutron stars or black holes. Theoretical and observational evidence suggests that stars cannot form with masses exceeding about 150 to 300 solar masses due to the extreme radiation pressure counteracting gravitational collapse. Similarly, below 0.08 solar masses, hydrogen fusion cannot occur, defining the lower limit for stellar masses. The mass of a star at birth determines its journey through the Hertzsprung-Russell (HR) diagram, a key tool in astrophysics that maps stars based on their luminosities and temperatures. Low-mass stars spend most of their lives on the main sequence, converting hydrogen to helium through the proton-proton chain reaction. As they age, they transition to red giants before shedding their outer layers and forming planetary nebulae, leaving behind a white dwarf core. Intermediate mass stars, like the Sun, follow a similar path but can undergo helium fusion in their cores during the later stages. After exhausting their nuclear fuel, they also become white dwarfs. High-mass stars burn through their nuclear fuel quickly, evolving into supergiants. Their cores collapse under gravity, resulting in catastrophic supernova explosions. Depending on the remaining mass, they may form neutron stars or black holes. Very massive stars with initial masses exceeding 150 solar masses may undergo pair instability supernovae, completely disintegrating without leaving any remnant. Despite its significance, accurately measuring stellar mass remains a challenge due to distance and resolution, as many stars are located at great distances, making detailed observations difficult. In multi-star systems, interactions between components can complicate mass determination. Changes in brightness, activity, or structure can affect indirect mass estimates. Theoretical models rely on assumptions about stellar composition and behavior, which may introduce uncertainties. In some cases, surrounding dark matter can impact measurements, particularly in dense stellar clusters. Stellar mass is also essential in the broader context of cosmology, influencing the formation and evolution of galaxies, star clusters, and the interstellar medium. The distribution of stellar masses within galaxies affects star formation rates, feedback processes, and the chemical enrichment of the interstellar medium. The initial mass function describes the distribution of masses for a population of newly formed stars and has profound implications for understanding galactic dynamics and chemical evolution. By studying the masses of stars in different regions, astronomers can infer the history of star formation and the influence of environmental factors. Merging neutron stars and black holes, remnants of massive stars, produce gravitational waves that carry information about their progenitors' masses. Advances in observational techniques and computational modeling are continuously improving our understanding of stellar mass. Telescopes like the James Webb Space Telescope and upcoming extremely large telescopes provide unprecedented data for studying stellar properties. The study of stellar oscillations offers insights into internal structures, enabling more precise mass estimates. Observatories like LIGO and Virgo are providing new ways to study stellar remnants and their mass distributions. Sophisticated computational models are enhancing our ability to predict and interpret stellar mass-related phenomena. In conclusion, stellar mass is a cornerstone of astrophysics, underpinning our understanding of stars, their life cycles, and their role in the cosmos. As technology and methods advance, our ability to measure and interpret stellar masses will continue to refine, deepening our grasp of the universe's intricate workings.